Okay, so we had stopped at this point in the previous video, and we shall continue from this point. So yeah, so now let us look at this graph. Okay, so I had said that the height of the derivative function represents the slope of the actual function here. So this height here at 1 represents the value of the slope of this tangent at x equals 1, and similarly this height here represents the value of the value of the slope of the tangent at point 2. So these are the two tangents, okay, the first tangent and the second tangent at so the two tangents are at x equals 1 and x equals 2 respectively, okay, and those two represent the height at x equals 1 and x equals 2 in this graph. Okay, now I can do that for all the points from here to here. So let's say if I take this point, let's say 1.5, somewhere in between, okay, so that height, the height at this point at point 1.5 will be this much, and I can go on this graph here and go at point 1.5, draw a tangent, so that tangent might look somewhat like this. That will be the slope of that tangent will be somewhere between this tangent, the tangent at x equals 1, and the tangent at x equals 2, and the slope will be equal to this height. Okay, so they are in a way the slope and the height of this graph, the slope of this tangent and the height of that graph at the same point are in a way the same thing. So the problem we had, the problem of finding the area of this thing had narrowed down to finding the average height from this point to this point of all those rectangles, and we just now saw that this can be represented by the slope of this graph, okay, of this graph at the same point by making a tangent. So now what we can do is, obviously it is difficult for us to take the heights of all these and find the average of all those heights, okay. So if I can draw all these rectangles, right, all these thin rectangles, if I can draw, so yeah, these are all those rectangles, right. So obviously I can't measure their heights and take the average, but what I can do is I can make the problem easier by representing them on this graph. So how do I represent them on this graph? Take the height and go on the, okay, so take the height, let's say at x equals 1, go at x equals 1 on this graph, draw a tangent. The slope of that tangent represents the height of the graph at the height of this graph at the same point. So by taking, okay, so I can do that with all these rectangles. Take the height, go at the same point and draw a tangent, and the slope represents this height. Obviously it'll be very messy for me to draw all those tangents, okay. So I'll just I'll just remove these tangents now, because they'll just make the whole diagram more messy. Yeah, sorry. So now, so yeah, and you all remember that, right? The slope is actually a number associated with a point. So this height is actually number associated with this point, which is the value of the slope, okay, value of the slope of the tangent at this point. So this height is represented by the slope of this point, this height is represented by the slope of this point, and this height, the next rectangle, is represented by the slope of this point, and so on and so forth. All these the slope of all these points, if I can find them out, okay, will be these heights, right. So now if I could find the slopes of all these points, take their average, what I would get is the average height of all these heights, because they're the same thing, they represent the same thing, right. But how do I find the average of all these slopes? So in another previous video I had told you that there are two ways of finding the average rate of change. One of them was to find the slopes, to take the slopes of all these points, add them up, divided by the total number of points. So in that way also we were finding the average of all these slopes to find the average rate of change. So whenever I find the average rate of change from this point to this point, what I'm doing is finding the average of all the slopes of all these points, and the slopes of all these points represents the height of all these rectangles. The slope of all this point mean the slope of the tangent at that point. Okay, so that is something that you need to keep in your mind. So when I'm finding this average slope of all these points, I'm finding the average height of all these rectangles. So if I find the average rate of change from this point to this point in this graph, what I'm actually end up getting is the average height of all these rectangles of this graph. So how do I find the average rate of change? Will I go to this point, right? This is the y value at this point at x equals 1, and then I go to this point. I just remove this. Okay, so this is the change in y, the y value, and this is the change in x. So if I can find delta y by delta x, so this was the second way of finding the average rate of change. So now my aim is to find the average rate of change, because the average rate of change of this graph represents the average height of this graph. A very complicated thought, but I hope you can digest this somehow. And the second way of finding the whole thing was dy by dx, and that is very easy for me to do, right? I can just take the change in this, divide that by the change in my x value. And how do I do that? Well, so how do I find my delta v by delta x? That will be simply equal to, so I'll just remove this word here. Okay, how do I do that? Well, I find the y value at this point, which will be, so instead of writing 1 and 2, I'll write x1 and x2. Okay, to keep this in variable form, nothing complicated, right? So at x2, if I go and find my y value is x2 whole cube by 3. Okay, because this is my function, x cube by 3. So at x2 I get x2 cube by 3 minus, so if I have to and now if I find the value of my y value at x1, what do I get is x1 cube by 3, because that is the y value at x1. So I subtract the y value to x1, which is x1 cube by 3, and this, by subtracting this, I get this change in y, and I divide this by the change in x, which is simply x2 minus x1. So now we finally got our dy by dx. Okay, so this is the average rate of change of this graph from this point to this point, and this also means this is the average of all these values of slopes of all these points. Okay, so if I have drawn the tangents at all these points, found their slope, taken their average, I would have ended up with this whole number. Okay, whatever I get by solving this. And so, and that also means that this is the average height of all these rectangles from 1 to 2. Okay, from but now there's no 1 to 2, so I have to write x1 x2 here also. Okay, x1 x2, I have to keep the limits, the boundaries same, right? So for when I had 1 and 2, I had 1 and 2 there also. When I have x1 x2 this side, I'll keep them x2 x1 x2 that side also. Now, so this means this number represents the average height from x1 to x2 of this graph. Average height of this graph, average slope of this graph. So you have to keep that connection in mind. And now the rest of it is fairly simple. So I'll just remove, sorry. So I'll just rub this whole thing here, because I don't need this anymore. And now what I do is, so that is gone. Okay, but I'll keep this part here, because this is the main point of all doing all this. Now, how do I find the area of this? So I recall my rectangle, okay, with all those which I had made by joining all those strips, rearranging all those strips, and okay, so this difference was equal to this difference, right? This length, this width, and this width in this case is x2 minus x1. Okay, you can clearly see that x2 minus x1. So this must also be x2 minus x1. I know this video is going to be a bit long because the concept is a bit complicated. Please bear with me. And the height, this height is actually given by this thing. So this whole number, I'll even remove this part. Okay, I don't think I need to write this part. Okay, so this height is given by this expression here. Is given by this expression here. So this times this gives me the area of this, and this width is this much, and this is given by this expression. So to find the area, I simply multiply the two numbers. What I get is x2 cube minus x1 cube by 3 and whole upon x2 minus x1. So this thing multiplied by the width, this is the height, this is the width, x2 minus x1 in brackets, okay? And I can, because the two are identical, I can just cancel them out. And when I cancel them, they simply, okay, vanish. So I don't need them anymore. And what I'm left with is this. So this is the area under the curve of x square from x1 to x2. Okay, so this is the area from x1 to x2. And I think now I should stop at this point, and or maybe wait, I'll just give a last point here, and then we'll end the video. So I can also simplify this whole thing. I can just simplify by writing. So this whole thing was actually given by one expression, right, which was x cubed by 3. Sorry, x cubed by 3. So this was the expression that I used to find the area. Okay, so I'm just generalizing the whole thing. Whenever we had to find the area of this x square graph, we use this. But what we do is we actually just substitute two values, the lower value, the lower boundary value, and the upper boundary value. So how do I write that? So what I do is I just put square brackets and write the first value here, the second value there, x1, x2. Now how does solve this whole thing? Well, I just put in the values. At x2 I get this value, at x1 I get this value, okay? And this is how I can calculate the area of under x square from any two numbers. And okay, so this is the general way. You can just put those two numbers here, and then by plugging those two numbers in, I can find the area from any between any two boundaries. Okay, so keep this in mind, and we'll continue in the next video. Okay.